Thank you. Hello, everybody. So let's start. So we are here today to talk about two things I like, functional programming and Factorio. A very quick note about me. I'm a senior Scala developer. I've been studying with Scala since 2016, and I'm actually joining Zendesk very soon. So now about the topic, let's start. So what is Factorio? So if you have not played, Factorio is a game, basically, to give you a very quick summary. You crashed on an alien planet. The local fauna is not particularly happy about you being there. And well, you need to basically build a factory to build a rocket to get out of this place. So in a sense, it's rocket science. The interesting part about Factorio is that in order for machinery to continue producing stuff, you need to have place for storing its output, or else it will stop. It's really practical because it means that we will not flood everything with unused production. And it's also very practical for me because it's kind of look like some problems we actually have in programming. Which I will just talk about like right now, which is back pressure. So what is back pressure? Well, back pressure is when you have a very fast producer and a slow consumer, or just a fast producer that actually produce stuff faster than the rest of the system is able to consume. It can be a lot of things. It can be different microservices. It can be different threads, anything really. And since you're producing value faster than you consume them, well, at some point your consumers have a problem. And since we are working with bounded systems, you have finite memory, you have finite CPU, you have finite time. Usually the issue is that, well, when we have these kind of problems, you hit some limit. Like, for example, your system crash because it gets out of memory, right? One of the main solution to actually handle this kind of issue is to basically slow down production. So it's not always possible, but when it is, it at least allows your system to continue operating in a at least relatively normal way, even maybe slower, but at least relatively normal. At least it will not crash. That's why we are talking about this, because, well, there are actually several libraries that actually handle this kind of stuff, but there is one I really love and I really want to talk about, which is functional stream for Scala, right? So functional stream for Scala handles this kind of issue by having a pool-based model, meaning that you actually don't produce value, you pull value out of something. So if you have a DB, for example, you will get the next row on demand. So this is a really well thought and well designed library, and that's why I wanted to talk about it. So let's get started. So let's start with something simple. Here we have a simple mining drill, right? So this mining drill is we'll do really not so much. It just repeats an operation, which is the operation of let's mine something, right? But it will do it over and over again until there is nothing more to mine, or there is no room in the output. So let's represent that using Scala and using functional stream for Scala. So here we have basically two operations. We have the first one, which is mine iron, which is basically mining one chunk of iron, right? So for those of you that would not know about IO, basically in the context of this talk, you can think about them like futures. Basically, they are reproducible future. When the only difference is which is important, is that when you run twice an IO, it basically produces two values, while a future is cached. So mine iron will basically do something. It will basically sleep for 2 seconds, wait for 2 seconds, and then just produce a value, right? Then we'll basically do this over and over again. So I have not implemented the part where we actually run out of resources, but it would not be very hard. And basically, it will evaluate the IO. So basically call mine iron over and over again. So stream.eval would basically call an IO and give you one result. And repeat will basically repeat this operation over and over again. And I've just added a small method that basically allows me to run my program, because when you describe a stream or you describe an IO, you basically are not actually doing anything. You are just constructing a value that represents what you want to do, which is really practical. But no, we want to actually run it. So basically, we actually take 10 elements of the stream, and we basically compile it into something that is runnable, drain it of all existing value in the stream, so all 10 values, and run it. And if we run that, well, we can see that every 2 seconds, we are actually producing something, right? So that was a really simple example. It's just for getting started, of course. Let's try something a bit more different, a bit more complex. So we have a furnace, which is basically able to smelt iron ore into iron plates. If you look at it, it's some sort of function in the end. It's a function that takes time and iron ore and turns it into iron plate. So in a sense, it's a function that you can basically, in some sense, apply in a map, right? And there is actually a concept in FS2 that you can use for this kind of thing, which is basically pipe. So basically a pipe is you can think of it as a map for streams, right? It transforms a stream of A into a stream of B, right? Relatively simple, again. So let's do it. So again, we have this function that operates again only on one element. So basically turning iron ore into iron. And I want to insist on that because there is often this duality between operating on one element and operating on all the elements. And it's usually very practical to describe operation on only one element, except if you have good reason not to. And then only apply, so basically in the detail, you go for one element, and in the large, you go for a stream, right? So so we smelt iron, and basically what we will do. So if you have played with Scala before, you know map probably, which is the function that turn a collection of A into a collection of B, provided a function A to B. Well, we will basically do the same thing. We will use eval map to turn a stream of iron ore into a stream of iron. The only difference between map and eval map is that eval map will take an A to IO or an E kind of effect of B rather than A to B, right? So this allows us to basically run this, and we basically use through to take a stream and pass it through a pipe, right? And you can see that, well, now we actually are producing iron plates. But if you look closely, you will remark that there is a small difference between the picture I gave you, the picture of a furnace, and the CLI that is going on. And the difference is that, well, if you look at it, when you produce one iron ore, you actually produce one iron ore. And then when you have produced this iron ore, you will try to produce an iron plate, which is not what is happening here. Because if you look at it, you can see that the production of iron ore does not stop. It continues on and on and on, because actually the furnace has some sort of input buffer, which allows it to smooth issues with production. So let's change it a bit. And we can improve it and say, okay, right now, I would say, okay, my input, I will prefetch 50 values, prefetch n 50. So basically what it will do is that it will create a buffer in input that basically is able to hold 50 elements. And it will allow the input and the output to actually run in parallel. And here we are. And you can see that now I'm not limited by iron ore production. I'm limited only by iron furnaces. Okay, so now you can see that, well, actually, since it takes approximately twice the time to actually smelt iron than it takes to actually mine iron, I can have two furnaces that operate on one single iron mining drill, right? So let's go for another structure. Let's go for the transport belt. So the transport belt is a bit more complicated because what I want to do is be able to emit somewhere and actually take elements from two different consumers, take the element of one producer, right? So basically, I want some fan out. And to do that, I will use something that is called queue. So queue is a concept that was originally in a functional stream for Scala. Now it has been moved to Katz effect. But since it's really useful for a lot of things, let's still talk about it today. So a queue is basically a very simple, it's pretty much what you would expect. It's something that basically has 4 methods. So basically you can take, try, take, offer, and try, offer. Take and offer are actually synchronous. So it means that if you try to take where there is no element, it will block and wait for an element to be available. If you try to offer while the queue is full, it will block until you have room in the queue. And try, take, and try, offer are the asynchronous ones where you have to actually handle when something goes wrong. Like, for example, there is nothing to take or you cannot offer right now. So now we can implement this transport belt, and we can say, okay, so I will create my queue. So with this, like always in this kind of scenarios, basically there is basically when you create this kind of thing, since it's a side effect, most of this library wrap it into an IO. So what I do is basically I create the building, I build the blueprint of how I will create a queue in Iron Belt. And then in Iron Pipeline, I actually create the blueprint that will start by creating the queue. And then I have basically 3 separate processes. The first one will be the drill that will basically keep pushing things into the queue. And the 2 furnaces that will basically repeat the operation. I take into the queue, I take from the queue, and then I pass it through to the pipe. So here I'm using repeat eval, which is basically the same thing that eval.repeat. And the interesting part is that now I need to basically run all these streams together, and I need to do it in a relatively smart way. So basically what I want to do, I want to get a stream of iron. So basically I want the output of furnace 1 and furnace 2. That's why I will basically use merge on the 2 streams. So furnace 1 merge furnace 2, which means they will run and give you a result indeterministically from the first one or the second one. And then I still need to actually run the drill stream, because if I have nothing that is offering to the queue, well, basically my queue will always be empty. And if my queue is always empty, well, my stream does not work. So that's why I will basically add this concurrently drill, and concurrently drill will basically run the stream in the background. So it will basically run the stream in the background and doesn't care about the actual values produced, which there will be none since belt.offer does not give you any interesting values, but it will continue running. And you can see there that basically now I'm limited. So I actually creating 1 iron plate every 2 seconds, which means that I'm capped now by the rate of the creation of iron ore, which is what we wanted. So okay, so now we have this done, and so now we want again to continue building on this kind of stuff, and start with again more complex, or in this case not necessarily more complex scenario, but which are assembly machines. And assembly machines basically are really close to furnaces. So the idea of an assembly machine is that it basically take some element and give you back another item, right? Or it can take several elements and give you back one item. So we basically have 2 recipes in this slide. We have the copper cable recipe and the electronic circuit recipe. The particularity of the copper cable recipe is that it basically takes 1 element and gives you 2 elements. And the particularity of the electronic recipe is that basically it takes 4 elements, 3 of one type and 1 of the other, and give you 1 element. So let's start with the copper cable recipe. So for assembling copper cable, well, basically I take 1 copper and I give you back a list of cable, right? It's a list of size 2. I could have used a tuple, but there are several ways, of course, of do this to do this. Let's do it with a list because it's way simpler. And again, so basically my cable assembler is a pipe. It takes in input copper, it gives you back cable. Again, I'm using prefetch n to desynchronize because to decorrelate two. So because assembly machine have an input buffer. And the only difficulty is that basically, well, I end up with a stream of list of copper, right? Basically, when I do input prefetch n50 eval map assemble copper cable, I have a stream of list of cable. And so the easiest way to actually handle this is basically to say, okay, I will just flat map my stream in giving it a stream of cable. And basically I can, from a list of cable, I can get a stream using stream.emits. Stream.emits will turn a list of A into a stream of A, basically. Nothing extremely complex there. Let's now talk about electronic circuits. So basically electronic circuits. So again, same idea is that basically I need 3 cables and 1 iron plate. So my function that actually handles the production of 1 circuit will not will not take much logic in it. So I will just break if I have an incorrect amount of cable. So here you can see that there is a chunk of cable. The chunk of cable is basically so chunk is a specific collection from FS2. You can mostly think about it as a list. In this context, it's approximately the same. Since I've got a list of cable and an iron, well, I can do my circuit assembler. Again, the circuit assembler will not handle a lot of logic in it. I will do the same things than with the previous assembler, basically saying, okay, prefetch n, eval map, etc., etc. But here the interesting part is about the circuit pipeline, right? Because basically what I need to do is to basically bundle a stream of copper cables into streams of chunk of copper cable. And to do that, you can it's actually really easy to do because you can use chunk n method, which will basically, so here it's chunk n 3, so it will give you chunks of 3 elements. And the second parameter is, do we allow of having chunks of of less than 3 elements? In our case, no, because we really want to have a hard constraint of the 3 elements cable. And then, well, we've got the iron pipeline that we defined earlier, which is basically something that gives you iron plates, and we basically zip the two. So here, so zipping a stream is the same as zipping a list. Basically, you have a list of A, a list of B, you zip them, you got a list of tuple A, B, right? Here's the only subtleties is that if you want to be coherent with the game, we actually need to parse zip them because zipping exists on a stream, but what zip will do is that it will pull from the left side, and then when it has an element, pull from the right side. That's not what we want to do. We want to be basically wait for both in parallel. So a parse zip will wait for one of the two. When it gets one of the two sides, it will wait for the other and then start again. And with prefetch, it will actually take regularly elements. And you can see it works. So when it will restart, you can see that at around 8 seconds, we will get our first electronic circuit. So here we go. Here's the first one. And you can see that everything is running in parallel. So I didn't mention it before, but I have actually used a copper pipeline that is basically the iron pipeline I defined. It's a copy paste of the iron pipeline. It's exactly the same thing. But well. So let's go for one other component. Let's go for splitters. So splitters are a really important part of Factorio. It basically does a lot of things. We will not cover all of them because there are actually several functions and which are pretty hard to implement actually. We will only care about two, the fan-in function. So basically you have two streams and you merge them into one. So here it's pretty easy because, well, as you've seen before, well, actually the functionality is already embedded in FS2. It's basically the merge functionality. So nothing much to say about that. But it was more about introducing the component. However, splitters have a way more interesting property is that they can actually filter elements. They can actually say, okay, I have a stream of several kind of elements, and I want to have end up with two streams, one of element A and one of the element of all the other elements, or in our case, it would just be element B. So this is actually a bit more complex to implement, right? So here we will basically aggregate a lot of concepts with seed, and we will actually use two queues to simplify that. So basically, I'm representing the left output and the right output as two queues, right? And basically, the output stream, and the left output stream and the right output stream will just be take from the queue. As you can see, I'm returning something that is a bit barbaric in its time signature. It's a stream of IO, a stream of IO iron, and stream of IO copper. Basically, the encapsulating stream represents the creation of the queues. Basically, it's the effect of creating a queue. It's necessary at the end. I will explain why. So basically, now that I have two queues, so you can see that I have basically a bounded queues, so of size 0. So size 0 basically means that I can actually only have one element ongoing in the queue. And then, so basically my filter will take the input and just depending on pattern match on the input and basically send it either to the right or to the left. Right. So once I have that, basically the idea is that I just need to give the left output and the right output in the output and in the stream, and then I still need to run filters. So basically I need to concurrently run filters. So basically filter will run in the background for the same reasons than before. If I don't do that, basically nothing will get inside the queue. And if nothing gets inside the queue, well, basically my filter will do nothing. And then I can run this. So when I run this, it's a bit harder to run because I get back two streams and actually need to do something with these two streams. So what I will do is that I will merge them back, but I will only take two elements of the copper stream or the left stream. And let's see what it does. So what you can see is that at some point, it just stopped filtering. Well, that's annoying, but the question is why? Well, actually, so the issue here is that since I'm taking only two elements of the copper stream, basically I have a blocked output. Since I have a blocked output, my process cannot continue. It will continue producing values inside all my buffers because, well, they don't know about the rest of the process. But since my copper stream is blocked, well, if you go back here, you can see that my write.take, or actually my write.offer, will end up with a full queue, and it will just block indefinitely. So that's something you need to care about when you are doing streams. There are still a few subtleties that you have to deal, but you have to deal with them in any library that actually handles streams. Okay, so here we go. And let's start. Let's do something a bit more complex now that we have all the concept required, right? So, I mean, this for Factorio is a pretty simple element. Yeah, no, we will not do that not because it's necessarily hard to do, but because we reach the limits of how much code you can fit in a slide or in this kind of presentation. Well, to conclude, Well, I hope that, so basically now you have built your factory, you have launched your first successful rocket, you're happy, so you are now a master of rocket science. So I hope that I encourage you to try a function stream for Scala. It's a really well-designed library. It's really interesting, and it's basically the same ideas and with functional programming. You basically define well-behaving components, and you basically assemble these components, and that's what we've been doing and doing and doing. Basically assembling components that basically know nothing from one another, but are still composing well because they are basically sane. And so you can really build really complex system with just small components that you have cobbled together, right? So, well, I guess that's it. So thank you for your attention. I've got the source of the code are available following the link, and the slides are also available following the link. So I thank you, and if you have any question, I'm available for a few more minutes, and I will be available in Spatial Chat just after that. Thank you.
Yeah, thank you very much, Kevin, for this really excellent presentation. And it appears that we don't have any questions in the Discord at the moment, so I think we can wrap it up.
Okay, perfect. See you in Spatial Chat.
Thanks again.